Okay, so we stopped off somewhere, and I said I was going to revisit this number before we continue. Here we are asked to check the dimension and basis for this particular set H. Okay, so and right, I have here defines the vectors. Okay, and that gives us okay, yeah. So from here, actually, or let's even use this place. So from here, it means that our vector 1 is actually equal to, of course, all the coefficients of A, which is 1 0 0, and then vector 2, all the coefficients of B, which is minus 3 1 2, and then vector C, or let's say V3, sorry, V3, all the coefficients of C, which are 1 minus 2 minus 1. Okay, so these are actually the vectors we want to determine their basis. The set of these vectors, we want to determine their basis and their dimension, and that's exactly what we have here as the columns of this matrix. And then by the time we reduced, so what we discovered is that our A, B, and C are all zeros. Okay, so which means that this particular vector is actually a null space. That means it has only the trivial solution. Okay, so the implication is that it has only the trivial solution here. So the basis it does not have a basis. So that's the implication, is a null space that has no basis. So it is only the null space. So the basis is empty. Okay, remember we don't put these two together. So the basis is empty, and if the basis is empty, it implies that the dimension is 0. Okay, so it implies that the dimension is 0. So, and the reason why it has no basis is because you can see that the solution is unique. So assuming one of these equations or one of the rows actually was eliminated, then you would have had infinitely many solutions, and that would have provided a possibility for a basis, even though the basis may not span the whole of the set or the whole of the vector space, but at least there will be basis. But in this case, it's unique, and then it's all equal to 0. So it's only the solution we have here is only the trivial solution, and so it's a null space with no basis, and therefore the dimension is 0. Okay, so that's the correction for that particular example, and then we move over to the next question, which is supposed to be from, I think, F or so. Let me check. That's 3E. Okay, so we are supposed to go to question 3E, if I am correct. Permit me to confirm that. Okay, it's not 3E. Is okay, we are still in 2. It's 2E. Okay, so we're supposed to be in 2E and not 3E. Okay, all right, yeah, and that's the last question. So now there is a last conclusion they said we should show there, that we should convince ourselves that that D is actually has no dimension, and the basis also no basis. Okay, so you heard what I said. You can just conclude there that since it has only the trivial solution, since H has only let's put it that way, since H has only the trivial solution, therefore, or hence, there is no basis, and dimension is 0, and the dimension of H is equal to 0. Okay, so that's a good a good conviction for us to make that conclusion. Okay, so now we move straight to the number E now. That's 2E. Okay, so for 2E, what's the question then? We are told to find the basis and dimension of the vector space. Look at it here. Okay, find the basis and dimension. Find the basis and dimension of the subspace. The basis and dimension of the subspace. So they've already told us that this one is a subspace, and they said they also called it H, and it's equal to, let me use this one, it's equal to the set of four representation of 4 vectors here. So we have A minus 3B plus C, 6C, and then we have 5A plus 4D, okay, and then we have B minus 2C minus D, and then we have 5D. Okay, so this is or these are the sets of vectors that, or what makes up the vectors where our A, B, C, D, okay, are elements of R. Okay, so and that completes the set of H. Okay, so this is what forms the subspace H. I think this happens to be the end of this. Okay, so that means we will try to take this to another page. Okay, so let's go to another page. Let me see if I can get that. Okay, have we moved? Okay, let me open another page. Okay, let me go back there and try. But first of all, let's increase this. Okay, okay, so we go back to the previous page. Maybe we should use this other one to cut. Okay, okay, so to add to new page. Okay, I think that's fine now. All right, okay, it's not aligning, but then that's fine. Okay, so that's what we've got, and that is our our E. All right, so here what is our expectation? Okay, so we are told to produce the basis and the dimension of this, and a hint is given there. So solution. Okay, so from the hint we are told that okay, so we can actually generate vectors from here, the vectors of this particular H. All right, and that was what I did in this F up here. So where I decided to bring out the vectors from the H that we were given here. Okay, so where I got V1, V2, and V3. Okay, so that's where we want to start from here. So, and that's what the hint started with. So let's try bringing out that. So they call the first one V1. And how do you get V1? Bring out all the coefficients of A. So you have 1, 5, 0, and 0. Okay, so because there is no A in the second and the last expressions here, and K, so V2 is equal to coefficients of b minus 3, 0, and then in the third one 1, and in the fourth one 0. Okay, and then v3 we call 6, 0, minus 2, 0. Okay, and finally v4 is equal to coefficients of d 0, 4, minus 1, and 5. Okay, all right. So, and then we are asked to get the basis and dimension for that subspace, meaning the basis and dimension for the set containing these vectors. All right, so remember we said that the bases are the vectors that are linearly independent. Okay, so can we get the vectors here which are linearly independent? Of course we can. There are first way you can go about it, which is also mentioned in the hint, is that you can see that v3 is clearly a multiple of v2. Okay, so you can see, okay, so you can say clearly our v3 is equal to 2 or minus 2 of v3, of v2, sorry. So is equal, is actually noted there. So, and if that is so, and you can see no other one is a multiple of each other here, so you can actually conclude that, and let's read that, and it says, and observe blah 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 that, okay, that clearly v3 is equal to minus v2, thus we can discard either v3 or v2, okay, and then retain 1, and we'll still have that this will be a subspace, you know, that will form a span as well on the vector space. Okay, so and then it says, or we can reduce to echelon form, and when they reduce, see what they got. Okay, so you discover that one what the vector 3 does not, that's the row vector 3, does not have a pivot, and so you can eliminate it there, and immediately you will discover that you will see something that out of these 3, so our v1, sorry, out of the 4, that our v1, v2, so since we discarded v3 from that reduction, then we will now bring in v4, that these are linearly dependent, sorry, independent. They are linearly independent. So someone else can decide to use v1, v3, v4. That won't still be bad, because you can actually switch row 3 and row 4 in that row reduction. So it's not a must that it has to be row v3. So any of those two can go. And so these are linearly independent. And if these 3 are the linearly independent ones, so we can conclude that the basis the basis for H, not of, okay, so the basis for subspace H is equal to our v1, v2, and then v3. Okay, so and then we will have that and so if that is our basis, then that automatically means that the dimension for that subspace is equal to 3. That's the number of vectors in your basis. Okay, so of course you can see the difference between this and the earlier question D that we did. Okay, so that in this case all your solutions are not all zeros, because you can see there from that row reduction. Okay, I didn't write the row reduction. If you write the row reduction that they produced for us here, they got something like 1, minus 3, 6, and 0. And then here they got 0, 15, minus 30, and 4. And then in the third one they have 0, 0, 0, 19. And then they have 0, 0, 0, 5. Okay, so of course if you can see that from here we have about how many free variables? You can see that R3 is a free variable, or sorry, your C, should we call it C or X3 or whatever, is a free variable. And then again, which other one is a free variable there? You can also see that okay, this one is not free, is a leading variable. Maybe other ones there too that you can see are free variables. And once you have a free variable, it means that all your solutions are not all zeros, so you can get many solutions from there. All right, and so that completes what we are told to do here. We've gotten the basis, we've gotten the dimension. So, and that is the end of question 2. Okay, so let's move over to question 3. Okay, I think I should increase this. Okay, so over to question 3. Okay, I suppose this is the size for this thing. That's why it didn't match with the other one I copied. Okay, sorry, not 4, 3. Okay, so for question 3 now, let's go. So we begin with the first part, which is A. It says, consider the problem of determining if the following system of equation is consistent for all B in R3. Okay, so let's see. And this is the system. X1 minus 2x2 is equal to B1. And then the next one is minus 5x1 plus 3x2 is equal to B2. And then you have 3x1 plus x2 is equal to B3. Okay, and so we are told to check if the system will be consistent for all, okay, for all B in R3. Okay, so if you choose any B that will contain B1, B2, B3 in R3, will it form a solution for all such B's? Okay, so let's see how that is going to be. Okay, so first of all, in determining it, they now took some steps, and in the steps they started asking questions. So first they said we should define appropriate vectors and restate the problem in terms of span. Okay, so like what we did in the previous example, from here we can define the vectors. And so the vectors are going to be vectors v1, so which are the coefficients of x1. In the other one, they were coefficients of a, then v2 coefficient of b, and so on. All right, so here we are going to have these as coefficients of x1, which are 1, minus 5, and 3. And then v2 will be coefficients of x2, which are minus 2, 3, and 1. And then again, you have the constant side, which is your b, okay, and your b are, okay, they are given as b1, b2, and b3. No values were given there, okay. So, and then to state this in terms of span of v1 and v2, so we want to say that we want to determine. Remember, they said we should determine if, where is it now? Let's go up. We should determine if the following system is consistent for all B in R3. So in other words, what we want to determine is if V1 and V2, if they span your R3. That's actually what we want to do. We want to determine if V1 determine, let me put if, determine if V1 and V2 span R3. Okay, so, or you can just say we want to determine, or we can say we want to determine if the span of V1 and V2 is equal to R3. Okay, so in other words, we may not need to write this one as a set. We can just say if V1 and V2 span R3. Okay, so or like this. All right, so that's what it means. Of course, if this spans R3, what it means is that for any set of 3 numbers you pick from R3, it will always help to form a linear combination of this. Okay, so that's it. And that's what this question is asking. So they ask that we should restate it in terms of vectors and span of R3. Okay, so and that's the answer for that first part. Okay, and then the second part is they now said we should find the solution of the system. Okay, so we should solve that system of equation that they gave above. Okay, solution of the system. All right, so how do we do that? We will try to do our row reduction. By now you should be used to row reduction. So let's bring down our vectors. What we got, how many elements? 3. Okay, so we are going to form the system now, which is going to be 1 minus 5 and 3, and then here we have minus 2, 3 and 1. Okay, let me confirm that that is true. Yeah, 1 minus 5 and 3, minus 2, 3 and 5. Okay, and that is multiplied by x1, x2, and then of course is equal to our b1, b2, b3. Okay, so remember in doing our row reduction, we can either do it this way, or but whatever we are doing, we do it across on the matrix here and the matrix on the right, because this is now seen as a matrix. Or we can join this matrix here to become an augmented matrix and then do the reduction together. So either of the ways, or let's do it that way. So that implies that we will have 1 minus 5, 3, and then here we have minus 2, 3 and 1, and then under the augmented part we have b1, b2 and b3. Okay, the thing is that after the reduction we can still bring our b to the other right and then bring in our x. Okay, so what's that? Let's begin our reduction now. So let me move this here and try to reduce at this part. So what is my first reduction going to be? I want to make these 2 zeros. Okay, so how is that? That means I'm replacing only equation 2 and 3. So my equation 1 will remain the same. So what will be my equation 2? The algorithm is going to be R3, since it's negative, so I'm going to add, you see I'm writing R5. Okay, so sorry, R2 plus, then the coefficient here will multiply this, which is 5R1. Or you can say R2 minus 5R1, which will still give us plus. Okay, so no point doing that. All right, so if we perform this operation here, this is going to be minus 5 plus 5 times 1, which is 5. So we have obtained 0 here, which is what we want, but we'll do it across board. So 3 plus 5 times minus 2, that will be 3 minus 10, and that is minus 7. And then for the last row or column, you are going to have b2 plus 5 times b1. Okay, so we can close here. All right, and then the next one is going to be what will be the algorithm? The algorithm will be R3. Since both of them are positive, so subtraction will eliminate. Then 3 times 1, which will give us 3R1. So if we perform that, this will turn to 0. And then if we do it here, we'll have 1 minus 3 times minus 2, and that's going to give us 7. And then here we are going to have b3 minus 3 times b1. Okay, all right, beautiful. So we now come over here and then continue our reduction. So we will need to also eliminate this and make it 0. And if we don't mind, we may want to interchange the rows, but there is no point. So let me use white here. So let's make minus 7 our pivot now. So that means we are going to have, I don't need to shift this a lot, so we are going to have okay, row 1 will remain the same, minus 2b1. Row 2 will remain the same because that's our pivot now, so we have b2 plus 5b1. And then row 3 will now become, what will be our new row 3? Before I close this place, let's form our new row 3 will be, I want to eliminate this, just do r3 plus r2 because r2 is now our pivot, so this will give us 0 here. So I'm going to have 0 here, and this plus this is going to give me, okay, sorry, here will also be 0. So I'm now trying to get this place, which will be 5b1 plus minus 3 is going to be 2b1. I'm beginning with b1, and then I'll come over to b2. So just add these two together, b2 plus b3. Okay, so that is the complete reduction of this system. Okay, so at this point now, you can now begin to try. Remember, they say we should solve the system, so we have been able to reduce. So assuming there were values for b1, b2, b3, then we would have known how to go about it. But from what we have done, what it means is that the system is going to have a solution only if the system will have a solution that will be consistent, will have a solution, let me put it that way, if your last equation is true. So the only reason why our equation, our system of equation will have solution is if this last system is true, because if we transform this back into our system of linear equation, what we're going to have is, of course, these two will now turn to x1 and x2. So we're going to have x1 minus 2x2 is equal to b1. Then this one will become minus 7x2 is equal to b2 plus 5b1, and then the last one will be 0 is equal to 2b1 plus b2 plus b3. Okay, so this system will only be consistent, that will only have a solution if this last equation is true. But if it is not true, that means the system is inconsistent. It's giving you an untrue equation. So it will only have a solution when 2b1, remove that dot there, plus b2 plus b3 is really equal to 0. Okay, that's when you have a solution. And then the next thing now is to now, if that, assume that that happens, so what does it mean? Okay, so what it means is that for it is not all values of b1, b2, b3 that will produce a solution, because some of them will give you 0. All right, for instance, if I make all of them 0, 0, I'm going to get 0. And if I make, for instance, b to be 2, sorry, b1 to be 2 and b2 to be minus 1, b3 to be minus 3, that's also going to give me 0. So it means that the system will not have solutions for some values of b in R3. And so you can define the thus. This implies that v1 and v2 do not span, v1 and v2 does not span the whole of R3, does not span the entire R3, or you can say the whole of R3. Okay, so remember, that's what we wanted to achieve here when we said that we were told to determine if this spans this. Okay, so that is another way of trying to check, that there is a solution for the system. Where is the first question there? They actually, let me check it here. Okay, so the question actually said we should consider if the following system of equation is consistent for all, and that's what we have defined here, that it is not consistent for all values of b in R3. So our v1 and v2 doesn't span the whole or the entire R3. Okay, So by implication, our solution therefore, so which now implies that our v1 v2, meanwhile from here we can get our x1 and x2. Okay, see what I did here. So from equation 2, assuming that this is not 0, so the implication is that from equation 2, let me draw this way. So from equation 2, it means that our x2 is equal to b2 plus 5b1 all over minus 7. Okay, alternatively that minus can come up here to become minus then over 7, but you can leave it this way. And then our x1 will be equal to b1 plus, because this will come over this way, plus 2x2, so which you can substitute to get x1 plus 2x2 is going to be, remember, you are going to have 2 times b2 plus 5b1 all over minus 7. So that minus can come out here to give us b1 minus 2 will now come in to now be, remember brackets, it will now be 2b2 and then plus 10b1, okay, all over 7. Okay, so if we take LCM here, we'll have 7, and that will be 7b1. Then the minus will come across to give us minus 2b2, then minus 10b1. Okay, so and that is our okay, you can collect like terms finally. So, and if you do that, you are going to have that this is going to give us minus 3b1 minus 2b2 all over 7. Okay, so and that is the solution for our meanwhile, come up a little bit. I hope I didn't make any mistake here. Yeah, this is my x2. Is this x2 correct? Is this x2 correct? Remember my row reduction formula here. Let me be sure. Okay, yeah, it is b2. Yeah. Okay, so let's come back here. Okay, yeah, that's correct. Okay, so our b1 is also correct. Okay, so in other words, we can now write, if we bring that somewhere here, we can now write that our solution, let me let me cut that and bring it over here. Okay, no, they are all in 2 different places, so there's no point cutting. So let's just write, so our solution for x1 and x2 is going to be equal to, okay, so what did we get as our x1? Minus 3b1 minus 2b2 all over 7, and then x2 we got 5b1, okay, that's writing b1 first now, plus 5b1 plus 2, okay, sorry, b2 only, all over minus 7. But remember I said this minus can come up here and multiply these two. So, and this is our solution for, okay, let me write it that way, okay, so that it will be better. So let the minus be up, so we have minus here and we have minus here. Okay, so, and that's the solution to this problem. So in other words, what we're supposed to do here, because of our space, we can just write the row reduction up to this point, and then maybe up to this point. So solve here and then get this. So when we get that, then we state that the system will only have a solution if this is equal to 0, and then that means that only that v1 and v2 span not the whole of R3, and then we just state this solution. This solution is got, you can just write here from equation 2 and 1, from equation 1 and 2, we have that our solution is equal to this, and that's enough. Okay, so that is for question 1A, which is I and II. All right, so let's look at the next one. That is the B. So the is it 1 now? 3A, sorry. So the B now says compute this definition. Okay, and what is it? Oh, sorry, complete. It says let S, okay, let set S be the set of V1, V2 up to V3 up to Vn, or they used VR here, and so they are saying be a non-empty set, okay, of vectors, of course. Of course, we are dealing with vectors here, not normal numbers. Okay, of vectors, then the equation, the vector equation, this one, k1 v1 plus k2 v2, then onto kr vr is equal to 0, has at least one solution, namely, okay, so they are asking us to complete this statement. So what is the one solution that this one will have? Of course, because it's equal to 0, you will see that our K1, it will at least have one solution, which is the trivial solution. And what's the trivial solution? The trivial solution is K1 equal to 0, K2, that's all the K's will be equal to 0, up to KR equal to 0. So that means, remember, like I said, this kind of equation is called a homogeneous equation. So your homogeneous, this statement is invariably reminding you that a homogeneous equation will always have a solution. The only thing is that at most, or at least, it can have the 0 solution, which we call the trivial solution. So and if that is the only solution it has, that's when we say it is linearly, the vectors there are linearly independent. But if it has other solutions, then you say the vectors are linearly dependent. And I think that's the second question. So they called this equation that we wrote here star. And then they said if star is the only solution, if star is the only solution, then S is called, that's the set of those vectors, is called linearly dependent sets. Linearly, let me use this one, okay, it's called linearly independent set, okay. So, but the implication is that, remember, they put set in the end, so the set is part of the question. So let me use white. So the one in yellow in this case is your solution, while the one in white here is your solution, okay. So meaning if they had said if star is not the only solution, then S is called linearly dependent, okay. So that's what you just need to note. All right, there is a third question there. It says if there are, like, you see what I just said is even here, okay. So if there are other solutions, if they are other, I've omitted R here. So if there are other solutions, then S is called linearly dependent set, okay. It's called linearly dependent set. So that's very, very beautiful. Linearly dependent set, okay. So and that's the solution for the I to I3, okay. So we move over then to C, and then C says that Remember the one we did now is B. I hope I wrote that there. Okay, I did. Okay. So this one is just applying your understanding of linear dependence and independence. Okay. So let's go to C. C says, with good reason, determine if set. Okay. Determine if set S equal to V1, V2, where our V1 is equal to 3 and 1, and then V2 is equal to 6 and 2. Okay, that's the first part, I. And then our V1 is equal to what is there, 3 and 2, and our V2 is equal to 6 and 2. Okay, so they are saying we should determine whether they are linearly independent or not. Okay, I would have loved it that they used dependent, whether they are linearly independent or not. Okay, so what can we do here? I think that's the end of this board. All right, so let's finish up here for that particular question. So how do we determine? So for, let me use this. So for I now, I can actually put solution here if I want. So for I, which is the first one, you can clearly see, we have been saying it before now, that once any vector is a multiple of another, then both of them are linearly dependent. So we can see that V2 is equal to 2V1. Okay, you can put since here. Since V2 is equal to, if you multiply this by 2, you will get this. So it only implies that V1 and V2 are linearly dependent. Okay, linearly dependent. Let me stop there. And then for the second one, okay, for the second one, we can say, since of course you can see there is no multiple relationship here. Okay, so this one, since the two of them, since V2 or V1, since V1 or V2 is not a multiple of the other. Okay, how should I write it? Since neither V1 nor V2 is a multiple of the other, okay, of the other, then V1 and V2, that's in example 2 now, or question 2, are linearly independent. Okay, so I will stop there so you can conclude that. Right, so they are linearly independent. Okay, so that's for that particular one. And then we move over to the next one, which is question D. So we have done C now. So D says we should let U be equal to the vector 3, 1, 0, and V to be equal to the vector 1, 6, 0. Okay, right? And then it says describe the the set spanned by U and V. And I says explain why a vector W is in span UV if and only if set UVW is linearly dependent set. Okay, all right, so let's see for question I, which says describe the span of U and V. Okay, so let's, from the solution they gave us there, the hint there, it says that 1, since neither is the multiple of the other, U and V are linearly, okay, actually there is a space there for you to fill in something. So since neither is a multiple of the other, you can see none of this is a multiple of the other, then U and V are linearly, and then they put dash there, so you should fill it in. And I've been saying that before now, linearly independent when they are not multiples. Okay, and then it says therefore it spans a plane in R3. All right, so it spans a plane in R3. Okay, and then what is that plane? So to describe the plane spanned by U and V means to write down the equation of the plane that has U and V. Note that the normal is U cross V. Okay, so we we solve these exercises following what they are giving us, because what they give us is where they ask their questions from. Okay, so they said that the next thing we need to describe is that the span of U and V is going to be a plane, and to get that plane we need to get the equation of the plane, and to get the equation we will need the normal to the plane, and the normal to the plane is U cross V, which they asked us to get. And what is U cross V? U cross V is simply the determinant of let's go this way, I, J, K, and what is U? 3, 1, 0, V, 1, 6, 0. Okay, so that means we are going to have I, remember, plus minus plus, so I is going to be 0 minus 0, which is 0, and then minus J is going to be, you cross here, 0 minus 0 also, which is 0, plus K, you cross here, which is 18 minus 1, and that is 17. So your U cross V is 0, 0, 17, or you can just write it as 17K, right? So this is what you fill in that space that they provided for you. So because I assumed you did this somewhere. All right, so now that we've gotten the normal, then we can use it to get the parametric equation, all right, for the plane using one of the vectors. So let's use U. Okay, and if we do that, we are going to now get that this implies that the plane passing through, if we use U equal to 3, 1, and 0, is going to be giving us, okay, the plane passing through with normal, okay, with the normal we just found now, with normal vector as 17K is, so that plane is going to be, let me bring this up, okay, where is it? Okay, all right, so that plane is going to be 0. Remember, you use the normal vector as coefficients. Okay, so 0 into x minus this, the x component, then plus 0 again, which is this one, into y minus the y component here, then finally plus 17 into z minus this 0 component here. All right, and that is equal to 0, so which is going to give us 17z equal to 0 is the equation as the equation of the plane. So I can write it this way. This implies that 17z is the equation of the plane. Okay, since they went through the root of plane in solving or describing the vectors that we are given. Okay, so that is the root, the equation of the plane. All right, and that answers the question for the first one, where we are told to describe the set spanned by U and V. So the U and V spans this equation of this, it spans this plane with this particular equation. So that's what that means. Okay, and then the II says that we should do what now? That we should explain why a vector W that is in the span of UV. So it's saying that if W is in the span, okay, let me write it mathematically. Okay, so if W is an element of the span of uv. Okay, so we are asked to state why this okay, or let's put it this way. W will be in the span of uv if and only if and only if UVW is linearly dependent. Okay, so that if you pick an arbitrary vector from a vector space and you are able to show that it is linearly dependent to the span of the vector space, then invariably that particular vector is also a member of that span. Okay, so let's now see that. Okay, so we okay, so that the only way that this will be in the span is that this will be linearly independent, and of course we can begin to see it. Okay, so from the hint they have there, they said if W is in the span of U and V, so it implies that okay, if W is in the span of U and V, so it implies that W can be written as a linear combination of U and V. And if that is true, that means they are linearly dependent, of course. So if which implies that UV and W are linearly dependent. It's obvious, okay, because if you say that it is in the span, so that means that W can be written as a linear combination of U and V. And if it can be written as a linear combination of U and V, therefore you can say that three of them are linearly dependent. That means I can write W as a multiple of V, and I can write it as a multiple of U also. So that means they are the three of them are linearly dependent sets. Okay, so and then he's now saying we can now present the argument, which is what I just presented. Okay, so that we are saying that suppose, okay, so let's now assume that, okay, or let me use assume. Okay, let us assume, so assume that U, V and W are linearly dependent. Okay, so I'm going from the back up now. So assume that they are linearly dependent, okay, or dependent sets. Then what it means is that one of the vectors or some of the vectors, then some of the vectors in U, V and W, that's this set, must be able to be written as a multiple of each other. Okay, is the linear combination of the orders. Do you get? Okay, so that's just what I said now, is a linear combination of the orders. Okay, so because that's the only way you can say that they are linearly independent. Remember, we have been seeing examples like that. So if they are linearly dependent, then at least some of them can be written as a multiple or a linear combination of the others. Okay, so the vector there, so what it means, full stop, and the only vector that can do that, the only vector there, the only vector there that can do that is W. Why is it so? Or should I say must be W that can do that? Must be W. And what is the reason? The reason is simple, because you've already said that U and V span is a span of where did they say that? Look at it up there. They said explain why a vector W in the span of this blah 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 is that. Okay, so we have already shown that u and v are linearly independent. So if u and v are linearly independent, then they cannot be written as a linear combination of the other. All right, so the only way you can write one as a linear combination of the other is that there is linear dependence. And the only way you can now achieve that is that w, which you have introduced, must be the one that should be able to be written as a linear combination of the other. So w must it must be w since v and u are not multiples. So you can put that since v is not a multiple of u, or the other way around, is not a multiple of u. Okay, we have already said that. That means they are not linearly dependent. They are linearly independent. Okay, so thus is enough to now conclude that w is in the span. Okay, so we can now conclude. Let me use that statement. So we can conclude that if w is in the span, let me even put that if. Okay, we can conclude that if w is in the span of u and v, then the three of them, u, v, w, must be linearly independent. Okay, so must be linearly dependent, meaning that they must span the whole of must be spanned by u and v. Okay, so must be linearly dependent, which is what we are asked to show. So that's the only way that can happen. If not, it is not possible, because u and v are already linearly independent. So the only way you can introduce something that will be in their span is that thing should also be possible to form a linear dependence with them. All right, and so that's our argument for that. Okay, and that concludes D. Okay, so and then we immediately go to question E, which is the last for number 3. Okay, so and what is that? The E says that what will be the value of k? Let me write it. What value or values of k will w be in order? Will w be in order to be in the span? I think I need to shift now. Okay, let me try to be in the span of v1, v2, v3. Okay, so where v1 is equal to, I know that's the next thing, so they give us v1 1 minus 1 minus 2. Okay, and then v2 is equal to we have 5 minus 4 minus 7, and then we have v3 as minus 3 1 and 0, and then the w was given, and the w is minus 4 3 and k. Okay, so what's the question again? That, okay, for what values of k will this particular w be in order? What values of k will w be in order to be in the span of? Okay, so he's just asking what will be the value of k for this w to be in the span of these other three this thing. Okay, so and then we started by saying solution. Okay, so a hint was given. The vector w belongs to the span if and only if it is linearly dependent to other. It can form a linear combination of the other three. So that's what we just defined in D above. Okay, so and that's what they're asking us. So if and only if there exist scalars x1, x2, x3 such that you are going to fill a space there. So that's why I'm beginning with this such that, so you complete it, such that those scalars multiplying these vectors v1 x1 v1 plus x2 v2 plus x3 v3 will be equal to that w. That means you can write w as a linear combination of the three vectors. Okay, and when that happens, so your job now is to find the values of x1, x2, x3, and in doing that you will now be able to get the value of your k. Okay, so let's quickly do that. Right, so it says next set up the augmented system, solve to get that w is the span, okay, if k is equal to dash. Okay, so let's go. So in other words, if we set up these vectors, we are going in a matrix form. We are going to have something of this nature. One, of course, each of the vectors will form a column. So we have 1 minus 1 minus 2. Then we have 5 minus 4 and minus 7. And then we have minus 3, 1 and 0. And then remember, it has to be augmented. So you have minus 4. You're augmenting it with w, minus 4, 3 and k. Okay, so of course you know this is multiplying your x1, x2, x3, and that will be equal to this, your argument, if you want. Okay, so but augmenting it like this will keep the x1, x2 away. Right, so now we are going to reduce and then get the value of k that will help us get that. So what is that? What will be my row reduction operation? So for here, if I just add row 1 and row 2, it will eliminate. Remember, we are eliminating this. We are trying to eliminate this to get zeros there, and then later we eliminate this one to get 0 here, and so on. Okay, so let's go there now. So if I add r1 and r2, that will eliminate this. Meanwhile, r1 will be the same, so I'll bring it down. I have minus 3, and then here I will have minus 4. Okay, so let's go. So this plus this will be 0, this plus this will be 1, this plus this will be minus 2, this plus this will be minus 1. Okay, then this one, r3 plus 2r1 is what is going to help us eliminate. Okay, so and that's going to be, of course, this plus 2 of this will be 0. This plus 2 of this will be 10. So if you add it, you get 3. This plus 2 of this, that's minus 6. And then this one plus 2 of this will be k. And then 2 of this is minus 8. Beautiful, beautiful. Okay, and there are two things we can do here. We can choose to make this to become 1, but then there is no point since our leading the pivot here is already 1. So we can now try to form another row reduction. So, and in that one we'll be replacing only row 3, and that's going to be something of this nature. Row 1 and 2 will be the same. So here we have minus 4. Here will be 0, 1, minus 2, minus 1. Okay, and then here, so what will be the row reduction? I want to make this one to be 0 using the pivot, and so that's going to give me row 3 minus, since the signs are the same, so I use minus 3 times row 2. So if 3 multiplies this, you get 3, and then the subtraction will give you 0. So we go ahead to fill in here. So this will be 0, and then this will also be 0, and then this is minus 6 minus 3 times minus 2. Okay, and that's going to give you 6 minus 6 plus 6, which is also 0. And then on this side we will have k minus 8 minus 3 times this one, which is minus 1, and that's going to be k minus 8 plus 3, and that is going to give us k minus 5. Whoa, this is beautiful, beautiful, beautiful. Okay, remember to separate dot our augmented matrix. Okay. Oh, sorry, yeah. Okay, let me not shift that much so that I'll be able to finish this here. Okay, so from there now I will get that I can now solve this equation. But even without solving this equation, for this particular system to have a solution, which is when this is going to be linearly dependent, so I need to now get that my k minus 5 must be equal to 0. Okay, so that means for that to be consistent, k minus 5 must be equal to 0, which implies that k alone must be equal to 5. All right, and that is the solution that is required. So now you can now go up to where they made a statement and then said if k is equal to dash, so and then fill in your k as equal to 5. Now meanwhile, you would have to do this row reduction in the space provided for you. It's just about only 2 reductions, this to this and then this to this. Okay, and that is that for question number 3. So that completes question number 3 for us. Okay, and let me see if I should continue on this or we take a small break and then try to do 5. But I would have loved to do question 5 altogether here. Question 5. So this video is already 1 hour ago. Okay, question 5. How many subsections do we have, or sub questions? We are moving. We are through with question. Or what did I finish now? Is it 4 or 5? Is it 4 or 5 that I just finished? Okay, it's 3 that I just finished. Sorry. Okay, we are supposed to enter 4. Okay, so 4 has about A, B, C, D. Okay, all right, so let me leave 4 and 5 for the next section. All right, so of course you know that this particular work is requiring patience, so we just have to go through it gradually. Okay, so for that I'm going to be ending this particular one. So here we covered the remaining part of the gray area in question 2, and then we ended all of question 3 here. So we are going to question 5 and 4 and 5 in the next section. So see you then.